Hi, in this video, I will do a very quick introduction to cycloalkane, and we will describe them and some of their very basic physical properties. So first, cycloalkane have low boiling point, melting point, and density because they have weak IMF among them. They have low solubility in water because they're nonpolar, and they have low chemical reactivity because they have very even distribution of electron density in all of the just like the alkane. And when it comes down to cycloalkane, we can have various types of cycloalkane. They have different member in the ring structure. We can have 3-member ring structure. We can have 4, 5, 6, 7, and 8, and also bigger as well. And this would be the molecular model of some of this cycloalkane. And cycloalkane possess something that we call angle strength. And this is basically the energy that is associated because of the bond deviation from 109.5. So hypothetically speaking, all of the bond angle here should be 109.5 because all of the carbon in all cycloalkane are sp3, which basically have sp3 hybridization or their tetrahedral electron geometry. So therefore, ideally speaking, their bond angle is supposed to be 109.5. But as they adopt this ring structure right here, they are forced to deviate away from this 109.5 angle. And that is basically what angle strain would be. So the energy, steric energy, that is due to the deviation from the 109.5 degree in the bond angle. For example, the bond angle between the cyclopropane, this is 60 degree. So we can see this is a very big deviation from 109.5. And in the cyclobutane, in this case right here, it is 90 degree. And this is 108, and this is 120, and so on. There are many different types of cycloalkane with various member ring structure. And here are the stability of the different cycloalkane. So of all of them, in terms of energy, 6-member ring structure or cyclohexanes, these are the most stable in nature. And this is basically the explanation why that we will find 6-member ring to be very common in nature. And now let's emphasize on cyclohexane, because this is the most common types of cycloalkane that exist in nature. So cyclohexane is actually not planar. Although when we draw a Lewis structure, we see it look to be quite planar, it actually is not. And we'll see some of that in a little bit. And they have several different conformations to them, just like the other types of acyclic alkane that we have seen already. Some of the conformation are referred to as the chair conformation, and some of them are called the boat conformation, or the twisted boat, or the screw boat conformation, and also the half chair conformation as well. So these are the different types of names of conformation that cyclohexane can adopt. And some of them are in lower energy than the other. Of all of them, the chair conformation are the most stable one. And here are 2 examples of the chair conformation right here. So the reason why we call this the chair conformation is because it does look like a chair, a big chair, and this is why that we named this the chair conformation. And here are how the chair conformation are compared in terms of energy with the other types of conformation. So the chair conformation is more stable. The half chair will be the least stable. And again, all of this conformation arises right here because as all of this bond right here rotate in the molecule, then that's what they give rise to. So the half chair will be the least stable, and then we can also have the twisted boat, and also so here is the half boat, the boat conformation, and this is the twisted boat right here, and here the other half one. But we can then see that there are 2 chair conformation, and these are not the same conformation right here, and we then call them the flip chair conformation. So they are flipped with respect to each other, and they are the most stable one. And this is why that in nature, when we have a cyclohexane, they primarily exist in the chair conformation. And this is why that we need to do a lot of analysis and learn more about the chair conformation. So in the chair conformation, the eclipsing hydrogens are completely being prevented, and the carbon-carbon single bond are very much close to being tetrahedral or 109.5 degree. And this is the reason why the cyclohexanes in the chair conformation are most stable. And again, here's an example of it. And we could then see that when we look at the hydrogen between the two adjacent carbon, we do not find them to be eclipsing each other. So again, when we look at this C2 hydrogen right here and compare this to this, we do not find them to be eclipsing. These two hydrogen in this case right here are anti with respect to each other. And then again, when we compare this to the next carbon and the hydrogen on them, then we can see that we will not be able to find the eclipsing hydrogens on the two adjacent carbon. And this is why that they are the most stable types of conformation. So in conclusion, the chair conformation is strain-free and therefore most stable.